So we are almost ready to interpret the vibrational spectra, both the IR and Raman spectra of methane. But before we do that, there's one last thing we have to go over in this chapter, which is how to visualize normal modes. So, we know for methane that we calculate the normal modes are A1 plus E plus 2T2. And previously I showed you some animations of what these normal modes look like. Is it a symmetric stretch? Is it a symmetric bend, et cetera? Is it asymmetric stretch? Okay. And I alluded to the fact, actually I mentioned several times, that you can use group theory to actually figure out what these look like. We've already seen how you can figure out which ones are bends and stretches, but now I'm going to show you how you can visualize them. And so in order to do that, so we're going to use group theory to calculate what they should look like. So we're going to predict them. We have to use a new mathematical tool. We'll be using this in the future as well. And basically this tool allows you to visualize things with group theory. And this is called the projection operator. And so it allows for the conversion of molecular attributes to basis sets for the irreducible representations of the molecule symmetry. And so, like a lot of these math heavy concepts, it's best just to see examples, and that's the best way to understand how they work. For stretching vibrations, the attributes we're talking about here, these molecular attributes, right? These molecular attributes, those are bond length displacements, okay? For bending vibrations, what we care about are bond angles, right? Because in a bend, you're changing angles. In a stretch, you're changing bond lengths. So here's the definition of a projection operator. SI is a symmetry coordinate belonging to an irreducible representation I. That's going to be proportional to the summation over all operations of the character of the operation when it's applied to that change in molecular attribute, whether that be, in our case, a bond angle or a bond length. And so, really the key thing that I want to emphasize about this definition, again, we'll see an example of how this works, several examples. So, you don't really have to understand it right now because you'll see it through when we work through the mechanics. But is that this summations across all operations, okay? And we know that, just to be abundantly clear, all operations are not the same as all classes, right? Because a lot of different similar type symmetry operations are in the same class. So this is kind of, there can be a lot of operations in different point groups, and so this can be kind of time consuming to do. So we'll start out with something simple. We'll do water. And so we know before that we did the calculate the water normal modes, 2A1 plus B2. There were 3 of them because 3n minus 6, and there's 3 atoms. 3 times 3 minus 6, that's 9 minus 6, that's 3. And so we can do stationary bonds, right? So we label these as A and B. And then we can ask, what's the representation for stationary bonds? That's to figure out which ones of these are stretches. And so you can say, okay, I'm going to do identity. When I do the identity, bonds A and B stay the same. When I do a rotation 180 degrees, A and B flip. When I do a mirror plane through the XZ, A and B are going to flip. And when I do a mirror plane in the plane of the molecule, YZ, none of them are going to flip. So I'm going to get 2. Both bonds A and B stayed the same. I can reduce that using the formula, or this is a simpler enough one. You can just do it by inspection, right? You can see that A1 plus B2, if you look on the character table, is going to equal to 2002. So since we did this for stationary bonds, this tells us that A1 and plus B2 are 2 stretching modes that exist. The other A1, that's what's left over, right? Because we only have 3 total. The other A1 is going to be a bend. Remember that fundamentally all you have are stretches and bends. So there are stretches A1 and B2, and then we have a bend A1. And so what are we going to do here? We're going to now apply the projection operator. And so there's the definition. And so let's walk through this. And so we're going to first look at trying to visualize the stretches. Remember, the projection operator is all about visualizing things. And so we're going to call these delta L1, delta L2. Because to do a stretch, we're going to be changing the lengths of both of those, right? And so for an A1 stretch, what we're doing is we're going to be timesing the character, okay, of our operation. And so first let's look at A1, and then we're going to apply, we're going to do that operation. By the way, hat just means operation, okay? Sometimes it can be hard to distinguish between E, the identity, operation, and E, the Mulligan symbol, right? So I just put these hats here, that means operation. But then we're going to perform all the operations on this symmetry element Q. And so that in this case is going to be L1 and L2. It turns out you only have to do it on one of them. And so you can do this on L2 or you can do this on L1. And you'll get the same answer in both cases or an analogous answer. And then you're done. So let's do this on L1 here. So these again are the characters. So you can see I have 1, 1, 1, 1 here. Why? Because A1 is 1, 1, 1, 1. Then I'm going to do an identity operation on L1. Well, if I do an identity on L1, it's just going to give back L1, right? So that's here. If I do a C2 on L1, that's 180 degrees rotation. That's going to move into L2. So that's there. And it was 1 times L2 because there's a 1 in front of here. So it's just L2. Now I'm going to do a sigma V in the XZ plane. That's right there, XZ plane. So that's going to interchange. L1 is going to go to L2. So 1 times L2 is L2. And then we have 1 times sigma V applied to sigma V YZ applied to L1. That's in the plane of a water molecule. So L1 is just going to stay L1. So we have just L1. So we add this up, we have L1, delta L1 plus delta L2 plus delta L2 plus delta L1. That equals 2 delta L1 plus 2 delta L2. So what does that mean? That means that if you change the attribute, let's say you change the length of L1 by 2, by a factor of 2, so you increase it by a factor of 2, let's say, L2 is going to increase by the exact same amount, 2L2. Now, because they both increase by 2, you can just divide out the 2 here just to make it simpler. And so that'll get you an L1 and an L2. So your answer will be L1 plus L2. That's indicative of a symmetric stretch. If I go out on L1, I'm going to go out equally on L2. If I contract on L1, I'm going to contract equally on L2. So that goes up and down like that. Let's do B2. B2 we know should be an asymmetric stretch. So same deal here. We have the only thing that's changed in the formula is now the numbers in front. The coefficients in front now come from B2. B2 is 1, -1, -1, 1. So I have 1, -1, -1, 1. All of the logic about what flips or what doesn't flip, we already have gone through. And so you just got these negative signs in front. This ends up getting you 2 delta L1 minus 2 delta L2. That gets you delta L1 minus delta L2. So what does that mean? We just divided the 2 out again. That means we have an asymmetric stretch. When L1 goes up, gets bigger, L2 is going to contract. And similarly, when L1 contracts, it's a negative, so L2 is going to expand. So that's a asymmetric stretch, okay? You can do the exact same thing for bends. There's only one bond angle here for water, and so this is kind of boring. And so no matter what you do to this one bond angle that's in the center of the molecule, nothing's going to happen. You do the identity on it, nothing happens. You do a C2 on it, well, you're just spinning the hydrogens around the angle, nothing happens. And you do mirror planes, nothing happens. So you're going to get 4 delta angles, and that's just going to reduce to a delta angle. And so, the angle's just changing. There's not much you can do. It's a symmetric bend. There's only one angle, so you can't have an asymmetric bend when you only have one angle.